introduction. I'm director for MVA Space, that is the space-related competence center of the Italian Institute for the Future. On a number of arguments, a number of matters, and the Center for MVA Space, in particular, treat the space matter, of course. For the Future is a 12-year-old organization. We produce a number of publications. We treat different kind of also economic and even political in the ample sense, of course. And we have a number of competence centers, few competence centers dealing with specific for example, we have a hub called for all those thinking about the future. Okay, now Center for MVA Space is essentially dedicated to the dissemination of the space culture. We want to stimulate and want to let's say, support the evolution and the growth of what we call civil astronautics, as we have today the civil aviation. We do believe that very soon we will have a civil astronautics, and last but not least, it's a private utilization of the space assets and technologies, so stimulation of the user community for concern space. What we do normally on the basis, we say like this, on the basis of the signals that we detect from today activities on space, in our case, of course, we try to estimate what would be the future, the long-term future in particular, not trying to reproduce what other entities, space agencies, for example, and even others do normally, but trying to go beyond so longer term with respect to space agencies and things like that. So we set up normally, working groups or task force, things like that, in order to perform this kind of activities. And one of major points that we are very proud of is the fact that we normally treat any kind of argument on two major words: interdisciplinarity and intergenerationality. That means we put together people from 16 years to 80 and more years old people, from engineers to physics people, experts in physics, doctors, psychologists, economics, and things like that, as you see here. Of course, we do believe that it is important this period of time to get together to collect all the added value, all the ideas available around, let's say, the atmosphere, around the table, if you want. Well, everything is based on the statement that becomes day after day more obvious. The expansion of humankind in space has already begun. I do remember 5 years ago, even a bit more, that people said, okay, we have in space, normally 5, 6 people, 3 people, things like that. But in a few years, we will have 20 people. It's a matter of fact, as you know, that this year, by chance, occasionally, but anyway, we got the result of having altogether 20 people in space. It was an occasion, but very soon we will have continuous 20 people. And as soon as other years will come, the number of people living, let me say, or spending a number of days, weeks, months in space will increase. The Center for MVA Space has a number of projects dealing with different kind of things, going from dissemination of the culture of space, everything I said before, among the specialists, including training, including putting together partnerships and things like that. But also with Celestia Sidera is the program dealing with that. We have the equivalent project dedicated to young people, so EduSpace. We try to provide them fundamental elements as well as the stimulus to think about the future, and even to try to test, to touch a bit more concretely some of the issues related to space. But I don't want to go into all details. Just I want to mention that Orbitectures is the main project on which we are focusing today. Orbitecture is a working group, is a project that is dealing with space habitats, and more in general, the definition or the study in general of the what we call cislunar city, and we will see which are the major characteristics. Now, let's come back on our approach. So, which are the signals of today? And we see every one of you, every one of us knows perfectly each one of these images. Yeah, the wonderful International Space Station built years ago that is going to be, let's say, in a way, publicly terminated in 2030. Up to now, at least, and pass to another kind of utilization by means of involvement of private companies, etc. We have the Axiom modules that are being built and will be mounted on the International Space Station. Then it will evolve. We have the Lunar Gateway. So, and you see the philosophy of building this kind of infrastructure the philosophy is always the same. It's a novel evolutionary, or what we call bottom-up wave or approach. The logic is always the same. And what we say, it is essentially a juxtaposition of modules built on Earth, brought in orbit, and directly integrated there. We all know why we do that, but this is what we do. And it is still in our mind to continue in this direction. Even if you talk about the Martian settlement of Elon Musk, we are essentially the same kind of approach, not only as 100% done and being done in space stations, orbiting space station, but also in terms simply of architecture of the settlement on Mars in that case. Well, what we say that we set up the Orbitecture, the orbital architecture neologism we created years ago, in order to think differently. So jump in 50 years from now and think what could be the concepts. And there is one point that is very sharp, if you want, but we want to provoke, we want to stimulate the idea. The wonderful International Space Station, in terms of design, in terms of evolution design, is after all a Paleolithic design, very similar to the very first cars, as you know. So we think that we have to move. We have to make a step ahead, and so we have to think differently. And you can see just some results of our investigations, and you can see, fully different approach. You cannot build on Earth this kind of elements and then bring them to the space and then integrate them. You have to do different kind of things. And we are looking at this kind of approaches, different kind of approach. And so we have defined, logically speaking, main design targets that are minimize the weight per capita in space, of course, maximize the space per capita in space. Why we say that? Because, of course, the ISS is a wonderful piece of engineering. It's a wonderful piece of our life at the end. But nevertheless, it is a laboratory. I believe that very few people, if any, would like to live normally in a space like the International Space Station. So we have to think differently. So integration of different kind of activities, not only research, something that was and is still today inconceivable today in a architecture like the International Space Station. And last but not least, if we're thinking in the near future, decades future, we have to think about ordinary people living there, not only researchers, astronauts, people very well trained and things like that. We have to think, because we believe this will happen. There are signals of today that this will happen. This is being, let's say, done really right now. Well, so what we say that, you know, symbolically, 100 years after the first step of a person outside the Mother Earth, so a different, think about the words, it's fully different from the first step on the moon. No, the first step out of our Mother Earth. So symbolically, 100 years after that, so 2069 is a symbolic date, of course. We will have a cislunar city. So in the space between the low Earth orbit up to the moon, the moon orbit and moon surface, but also in some of the Lagrangian points, we will have a distribution of districts. Just to use the same wording we use on Earth, some district devoted to for the four of them. We will go back to this label shortly. I hope I have a signal that the internet is not very stable, but I hope that everything is okay. We have in particular studied from the architecture point of view, from the habitat point of view, two pieces. I will call them later on. But anyway, this is the Space Hub. It's called Space Hub, and then there is another let's say settlement on the moon that is more dedicated to industry. But we will come back to that. The last point I want to say on this slide is that, of course, there will be other elements other than the 12 districts coming from the actual, let me say, approaches. So the International Space Station or some other kind of evolution of them, the ones from Axiom or things like that, as well as the lunar gateway, that are designed for a limited number of persons. So this will be a sort of country villas. So integrated into the entire city. Just to anticipate, we say 1,000 people in the cislunar city, divided by 12 districts. So you can imagine that as a mean, each district will have 100 persons. Okay, let's go. Function, macro functions. First of all, and then later on I will tell you why. First of all, is industry. So mining, processing of certain kind of material, producing semi-finished product, even production of components for the cislunar city. So made in space, certainly, but also for bringing some products on Earth, as I would say, as I will come back later on. Research is certainly fundamental because, you know, it is by definition, even on Earth is fundamental, but in that case it's even more. And so we will have an important segment dedicated to research. Management because we will have a settlement, an important settlement, a big investment. So it will be necessary to manage in the generic sense, but also thinking about repairs, supplies, etc., but also maintenance, of course. And last but not least, all the other elements that are necessary for any kind of cities on Earth, and so is the same in space. So communication, transportation system, and everything you can imagine for what concerns the city. Resorts, that means habitats for hotels, for tourists, for homes, for houses. I mean, for even socializing areas. So canteens, bars, things like that. Everything we mentioned probably for the population we are thinking about. I cannot go into all details, but I want to show you just the estimation we did and the distribution of population and how many of them are supposed to be involved directly on industry, research, management, and gas, tourists, and things like that. And you see the numbers: 1,000, roughly 1,000. It is not true that we will be 100% research or 90% research. Cannot be done like this. I will tell you, and I can anticipate that is the economics. We cannot keep this kind of infrastructure alive just by research, or if you want, just by governmental supports. The costs are much higher than the governments can assure. So we need private involvement, private investors. We need commercialization. We need, according to the actual social life on Earth, the ones we know at least, we need that we need the production of goods and the distribution of these goods inside the Silicon City, but also on Earth, as already said. This is just a few words about the Space Hub. The Space Hub is a node, is a spaceport node, it's a logistic district that is supposed to be positioned in the Lagrangian point L1, just in order to support, it's a central, interchange, node to support all the activities and transportation and activities in general, life of the Silicon City. You can see here few words, few elements. We have the central bubble, the central sphere that is called Miranda. It has a diameter of 44 meters. Then it is connected with the toroids. You can see here the. Let me switch on my laser point. You see here the two toroids, and you see here how the Miranda is connected with all the toroid systems. We have 3 thrusts, and we have a sort of lift that are really lift, a bit different from the heart lift, of course, but they are capsule lifting people from the Miranda to the external part of the station. The 2 internal toroids, the twin toroids are located are dimensioned in a way that the 2 run per minute rotation produce lunar gravity in this kind of toroids. One of the toroids is fully dedicated to culture, to crops, because it is necessary, as you know, for sustaining the life in the entire station. There will be 6,000 square meters of crops to be continuously, let's say, supported, and in turn to support the life of 100 people, 120 people in the station. And then the external toroid is at 166-meter diameter. It simulates in a way, produce simulated gravity of the Mars environment. Among the toroids in this area, I suppose you see my pointer. There is a sort of a solar panel carpet, the dimension of which, and thinking also about the evolution technology of this solar panel, will be more than enough to support the estimated energy needed to have this district alive. Okay. The space hub. Few other words. You see here how it rotates. Essentially, 120 people will live systematically on this infrastructure. The shape is a planetomorphic. What I want to underline is that this shape was not defined a priori. We studied the boundary condition. We studied the requirements. We studied all these elements and arrived to this particular shape. So I want to underline this process. We made a concept and phase zero design activities, so we have essentially a prefeasibility based on the forecast and foresight of technologies. Many people say, first of all, how much is the weight? How much is the cost? How you bring all this material over there? Okay, we tried to a certain extent, of course, to analyze these elements because we want to propose, this is another characteristic of CNS, Center for Near Space, we want to propose something that is logic, not just science fiction, because science fiction is okay, it's a perfect contributor of ideas, but comes a bit later on. So the Miranda, let's say, ball is essentially made of an inflatable structure that once it is inflated, then it becomes rigid thanks to a number of processes using specific gases from the inside and using also the solar radiation from the outside. The toroids are built with additive manufacturing. So we studied a bit, a multi-head 3D printing machine. We called it TCM, toroid construction machine, and while the internals in general of the station are supposed to be built by means of the spider fab. That is something that NASA and other Americans proposed some years ago. You can see also the targets. The pressurized volume per capita is 4.5 times higher than the International Space Station, while the structural density is much less of the International Space Station. And last but not least, the closed-loop ECLSS is also estimated. We started, of course, from the actual technology, from the ISS systems, and we try to identify step ahead in order to reduce as much as possible the supply of water or food or other things from the external of the station. Other elements. This is a section of one of the toroids. The structure, the external structure is supposed to be printed in space in vacuum. I mean, with additive manufacturing. So it's challenging. But we believe that, of course, it is not available, this technology today, and it is not foreseen that this technology will be available tomorrow or in 5 years. But in 20, 30 years, we are confident that the signal today says clearly that this technology will be available. We let's say design single accommodation, single rooms for and some architects in our team says it's better to allocate permanent workers on a single accommodation, while double accommodation are more correctly, more efficiently allocated to space tourists. Space tourists are not just tourists in the traditional sense, but also people, guests of the working environment that are guests, that are present in the station for a limited period of time because they have to work with for any kind of activities on the station with the people permanently being there. This is the corridor for going from joining the different kind of room. Let me go for a while back. The corridor are two here. This is one corridor, and the other one is another corridor. Very similar to the corridor we have on Earth. And so we try to do the same. Of course, the dressing. This is, symbolically speaking, a traditional Earth dress. We will see what will happen. By the way, we are also studying a bit, fashion, space fashion. But the idea is to tend to push, to stimulate the ideas of the designer, the architect, the stylist, to think about common person having to work over there. We are too much accustomed, 100% accustomed to imagine anyone going to space in a very astronaut-like suit. So it's a very specific, it's a working dress. We have to go to pass over this. This is just an idea of a double accommodation room. Very well. Okay, this is another segment, another section of the entire the Miranda sphere as a cylinder for the hangar. This is the hangar where the spaceship arrives. Are subject to simple maintenance, refueling, things like that, and then fly back, fly another side. But we have a microgravity laboratory because there is the rotation axis over there. But we will have also other, let's say, less reduced gravity in general, different kind of level of microgravity. And then we will have the lunar labs located in somewhere in the internal toroids and Martian labs in the external laboratory. Because and this kind of labs, even training rooms for people that that will have to go to on the surface of Moon or on the surface of Mars. So they will be trained in order to get there in a more efficient way from the physical point of view. We have here single accommodation, more internal in order to be more in the center of the entire station. Double accommodation are mostly allocated on the external side. And then we will have also in all parts some condensation areas for socialization activities. These are all ideas to stimulate and to think about a different way of thinking or building or designing the habitats of the future. These are well-known, the crops and the activities and the modules for the cultivation for the crops. These are very much interesting, important, fundamental, paramount for let's say for edible foods in general, but also for production of oxygen and let's say elimination, partly at least, of non good gases, CO2 or something like that. This is most of this is the cycle and ACLSS, sorry, of the International Space Station, but we modified this part here in order to make a step ahead, a further step ahead. You can see here the solar panel carpet between the different toroids, and you see here that, okay, this is in Italian, sorry, but we need an estimated value of 2.6 megawatts for running this system, and we get from this kind of carpet about 4 megawatt of power. So it is feasible. This is another idea of the hospital, orbital hospital. Of course, for 100 people, 120 people, we don't need an hospital with 20 beds. We need a much smaller, let's say, let me call it again hospital. But we need of course this kind of capabilities and assets. This is This is the view of the control room of the entire station, if you want, and in particular, it is indicated the spacecraft here inside the hangar, and the let's say action, if you want, of a person that is supervising the maintenance operation between one flight and another. Now we pass to another part that we studied on the moon surface, so moon habitats in particular. But what we studied here was as I said before, an industrial let's say settlement. The position was identified by Moon Village Association during discussion we had some times ago. So in the south pole of the moon. And what is important from our side, from the architectural point of view, is to underline the differences in designing an habitat from between or among, if you want, the Earth situation, the space, and the moon. For Earth, today, after many, let's say, very long time of human life on Earth, we essentially are concentrated in satisfying the environment, the landscape, and the memory. These are three elements of our life, and designing the habitats on Earth mainly and more or less, of course, are dedicated to this kind of principles: environment, landscape, memory, if you want, in Latin, firmitas, utilitas, and venustas. In space, this cannot be done that because the situation is fully different. The space hub, for example, is essentially isolated, so everything must be thought internally. And our architect says, at the end, after all, if we examine the elements, the triad utilitas, firmitas, and venustas can still make sense in a fully different sense, in a fully different way, as I said, looking to the inside rather than thinking to the outside as we normally do on Earth. For what concerns the moon, the story is different because the moon is somewhat in between the two, somewhat, and sorry. And so essentially, we have to go there. We have to, in principle, to break the soil, if you want, and build our settlements. And as we will see in a moment, we are saying it is useless to do that. It is costly, it is time-consuming, and we also destroy the surface of the moon. So we can use a different kind of approach. I go here in a moment. Okay. You see here, now I don't want to go into all these elements. Our idea, our, let's say, design evolution, after some discussion, a number of analysis of requirements, etc., as I said, is based on the concept of minimizing the impact on the ground. And so it is not a new thing. It's something that the archaeologists on Earth do since centuries. So the archaeological approach means try to have structures, habitats that are posed on the soil, on the ground, with the building and the main part of the habitat suspended with respect to the ground. So in this way, we don't need to move reduce the ground to a flat situation, to move materials and destroy essentially the nature of the moon. So we also safeguard the nature of the moon. So the same is the stable core. The stable core is here depicted. You will see how it evolves. It's a sort of hemisphere of 50 meters in diameter, made of ice and regolith, because the regolith is over there, no problem, with a sort of double pack compartments, controlling the pressure, temperature, things like that. And this semisphere will contain many things. Don't forget, we're talking about an industrial building, if you want. But I don't want to go into all these elements, tables. We will have the chance to read it in details without problem. But I want to go a bit further. There are a number of phases. You see here, you have the points where the settlement is posed on the surface. We need, of course, a main element. So this is the only one that creates, in a way, let's say, interference, human interference with the surface of the moon. And we will also need this because of a number of functions. First of all, the lifting to the different floors where the activities have to be done, but also for other kind of functions. I don't see other words, functions. On top of the construction, we will have the greens, the crops, and everything's needed for production of oxygen, etc. Then we will, once we have built the main structure, the cupola and the legs, of course, we will start from the green in order to have immediate reproduction of oxygen. Then we'll continue building different floors upside down. I mean, from top to the floor. So the first element is this, and the other will come, as we will see shortly. You see here the external side of this level. You see, in particular, there is a lot of water used as protection, as radiation protection. So, and water is also necessary for the entire life of the situation. So that's the point. The water wall is 10 centimeters thick, and also this settlement is designed for 100 people roughly. Then one of these cupola can be even integrated in a modular way with others in case we need to have more activities, more people. And you can see here in the video how the different phases will come in time. In the meantime, I underline that also this district is supposed to have 120 people, and archaeology approach has already been mentioned. You can see here also some autonomous systems moving on the surface of the moon. We like the solution of Boston Scientific, but this is one of the others. Essentially, it's a sort of scientific mean of transportation for 5-6 persons moving outside of the industrial settlement to do activities around the settlement itself. Now, transportation of the entire lunar city. Of course, the orbits are symbolic or indicative. You can see that we have investigated and we have studied how many persons, how much cargo has to be transported, etc., etc. And so, coherently with the entire thing, and also with the economy that I will deal later on, we have identified 2 cyclers, the Earth-Moon cycler, so joining the Earth and the Moon, the Lagrangian circle line, the one connecting in a way or another the 3 Lagrangian points involved, and then the other lines, sort of local trains, if you want. If you go to certain number, you can see that we have identified some number, we have dimensioned this kind of thing. So assuming one single configuration of a transportation system, that could be this, but we have estimated that each terrestrial here, we will have 120,000 passengers running from one district to another, and more than 100,000 tons of cargo being transported from one side to another. And the major characteristics are the following. As I say, the vehicle is always almost the same for 10 passengers and 10 tons cargo altogether. There is a specificity for system leaving the Earth, going to the Sirastini. This kind of, in this case, we will have supporting boosters because of the strong gravitational field. We will have 22 operational transportation vehicles plus 5 for routine maintenance shift. So a full set of scheduled flights is completed 1.5 terrestrial days. That means 18 cycles per lunar day. That is, according to our even economic estimates, are numbers that are coherent with the technical and the technology, but the cost also. Let me, one word about, I have to run a bit. So this is an old graph. It's something like 10 years old graph, even more, if I will remember. There was the indication of the evolution of civil aviation in the last century, and where we were at the beginning of this century. 2.5 billion passengers. We are today to 4 billion passengers. And here was, at that time, the estimation of the entire space transportation, so civil astronautics altogether. Forget about the separation, we do not have time to go into detail, but essentially what I want to underline is that the estimation is not far. I would say that it's very similar to the airline passenger evolution of the last century. So this has to be expected, and we have to be prepared for that. The economy. Last slide of my talk is about economy. Economy has 4 major, let's say, chapters. One is transportation, industrial system, the tourism system, and the science and technology research systems. There are a number of things. Most of them have been already mentioned in my previous slides, so I will go over. And we have some numbers. We have tried to estimate these numbers. What I want to say, this is the annual budget in the year 2070 at the present economic condition. And you see that the cost per annum of this infrastructure is $370 billion or euros, is the same. This is already per se an interesting number, important number. That per se means that the space agencies cannot afford this cost. So that's the reason why it is important to have a private component and commercial activities. What is more important to a certain extent is that the most 90% of this cost is related to the infrastructure management and maintenance of the infrastructure, not initial investment, just maintenance. This kind of number that have been estimated more or less with the actual, rules on Earth, of course, with some extrapolation to the new situation. So 90%. So to have this city living, we need to spend most of the costs associated with the entire budget. So for what concerns the revenue, if we don't consider industry for the first step, let's say, you can imagine, you can see that all the other activities, even if we consider film sets, advertising, everything we want, we will never be able to cover the entire cost. So we need underline 3 times that an industrial activity is set with the new commercial activities. This is in terms of cumulative economic flow from the beginning of the story up to year 2070, and you can see here that let me go directly to the last point. We have almost an estimation of 60 trillions euro, including what is called what today is called the new space economy. Essentially, that is made essentially even more than 90% on Earth, for Earth. The communication on Earth, Earth observation, and things like that. But include also something for the upstream, of course. You know that this is the estimation up to the year 2040 of this number. That the in year 2040, the best estimate today is around 1 trillion. Just correlating with anticipation, let's say rules. Let me say very simply like this: we anticipate that. Sorry, there is something wrong here. Sorry, there is an error here. This is 1 trillion. We have to go to 15. We will go to 15. Sorry, the graph is not correct. I'm sorry for that. But what is important that, including every kind of things, we imagine to estimate the overall cost up to year 2070 evolving like this. This is not incoherent with the estimation made by others, but to a shorter terms, like China, like in the United States, and like international bodies, all are estimate something in this fork, let's say, of lines. And this kind of extrapolation are made by us arbitrarily. So while our estimation is made of some more analysis. So, and the 60 trillion euros represent the present world GDP. I want also to underline one more point, is that if you think about SpaceX is a value of in the order of 30 billion per year. That is only one third, less than 1/3 of the annual budget of FCA, the automobile company, that is even not one of the largest. What I want to say is that there is space. There are entities, industrial entities on the world, on Earth, that are economically strong enough to be involved in this smart city evolution. We do not have only to wait to Elon Musk equivalent, but there are a number of other actors, several at least, that are the capabilities to be involved on this kind of economic situation. The last point I want to mention here, even if I have still some minutes, is that if you look at the long story, we have mankind has lived a number of long wave of investments, starting from the age of the textile and canals, and then the age of steam and railways, and then the electricity and heavy engineering, etc., etc. All this line, more or less, has a life cycle of 200 years, something like that, 200 years. So we do believe that that age of space industry has already begun, as we said, and this will last certainly up to 2125 or so. So we are just in the middle of this, just at the beginning, sorry, at the beginning of this important long wave. Okay, this is my last viewfoil. If I have time, I just want to run on a couple of pictures, because starting from the space hub with the toroids and with the central bubble, we also measure ourselves. We challenge ourselves to think even more in the future, but it is not really an exercise for the future. It is just a dream, if you want. We studied what we call Orbitech, that is 10,000 inhabitants, positioned somewhere. Forget about Leo. I mean, it could be any place. The configuration is made of 5 space hub plus. So a space hub, as I said, is 100 people station. Scaled up to 2,000 people, and then we have 5 of these. We try to study this, investigating a number of elements. Of course, it was not investigated everything, of course, but we identified also the docking parts. We have a number of elements. The propulsion system for orbital station keeping, and then we have also some consideration about the internal distribution of labs or habitats and things like that. We also studied a bit some more futuristic habitats, but continuing exactly the same logic and the same philosophy that I have expressed and have illustrated before. You see here a section of the toroids, similar things, but more larger, of course. The habitats are much larger, so are more similar to our houses and things like that. You have here the docking, the dry dock of the entire station for a number of spacecraft, of course, arriving and then leaving. And this is the overall, picture of the entire system, just to stimulate a bit the imagination of what could be thought for the long term. We don't know in which point in time could be positioned.